Okay, thank you for joining so late today in one of the last talks. And I'm going to talk about static code analysis and what I did in the last 3 years as research as part of my PhD. And we will see how to detect automatically security bugs in PHP code. So I'm going to give you a short introduction why I have this strong focus on PHP. And then I will go over to introduce a general approach for static code analysis I chose, and then how to detect first-order bugs, the traditional security bugs, and then second-order vulnerabilities. And at the last step, I'm going to talk about how to detect PHP object injections and generate gadget chains for those security vulnerabilities. So shortly about me, my name is Johannes. I used to tweet a bit with the nickname Fluxfriners. I have a web blog, and as I said, I did my PhD at the Ruhr University in Bochum. And I worked as a security consultant, and I was a passionate capture the flag player. So this soon led to the desire of automating things. So I wanted to detect security bugs automatically in code. So I'm the initial developer of RIPS, an open source tool for static code analysis of PHP applications. And now I redesigned the whole tool, and it's part of a startup in Bochum now. So here's a little research timeline. So I began almost 10 years ago to play with those little regular expressions. So I have to say in 2007, the PHP applications were more the PHP scripts, so it was a bit more easy. Still, I failed miserably with my regular expressions, so I stopped doing that. Well, it was enough for capture the flag contests, but it wasn't really enough for analyzing real-world applications. So I began playing with tokenizers and released the first RIPS version, which is still open source, but still it has fundamental limitations that lead to false positives. It doesn't support object-oriented code. So I redesigned the whole tool again during my master thesis, and then in the past 3 years I refined analysis and researched new code analysis techniques, and now it's available as a product. So why do I focus on PHP for so long? Well, that's relatively easy to say. PHP is just has like a huge market share. It's run on 82% of all websites. The OWASP website, for example, uses WordPress. That is PHP, just as an example. And as a security researcher, it's also fun, as you guys know. It has lots of oddities and pitfalls. We heard that in previous talks. Developers implement security vulnerabilities more likely in PHP applications than in other languages. So in the CVE database, actually 25% of all those already reported and documented vulnerabilities are related to PHP, which is quite a record to make. And in a recent study in the website hacked report, they found in 97% of the hacked websites they analyzed, I think it was about 11,000, that there was a PHP CMS running. So there's quite some motivation in analyzing PHP applications. The problem now is for today's PHP applications that they get more complex. And if we want to detect security vulnerabilities in those complex million lines of codes, then the manual audit becomes sometimes inefficient, right? So here you see a core graph of the WordPress index page, which is quite a mess. And you can imagine how difficult it gets to detect security vulnerabilities then in even huge or more large applications. So the approach we are taking here is, as I said, static code analysis in order to automate the detection of security bugs. And static code analysis has the huge advantage that we have full code coverage. So we want to detect all security vulnerabilities in the whole source code. And static code analysis is able to analyze all different execution paths of an application, while dynamic code analysis can only analyze the single execution path that is actually run during analysis. And obviously the disadvantage of static code analysis is that there can lead to false positives, because a software in the end cannot always decide correctly about another software. So we're limited by the halting problem, and we have to base a bit upon assumptions. So we will always have some sort of false positives in the worst case. Okay, the challenges specifically for PHP. PHP is highly dynamic. You have code evaluation, you have reflection, you can dynamically include code, and you have a variety of language features. So PHP comes with, I think 5,700 built-in functions are documented. If you're missing the analysis of one of those built-in functions, then your data flow will not be analyzed correctly and you will not find vulnerability correctly. And we have complex vulnerabilities, as we will see later on. Next to the traditional types, we have those second-order vulnerabilities we want to detect and those nice gadget chains for PHP object injection. And this is our research goal to detect those with static code analysis. And the main challenge here is to not only find an approach that works, but also find an approach that scales to large applications, right? So it doesn't make sense to find an approach that is really precise but takes like 1 year to analyze an application. You want to be really fast and quick to even build it into the SDLC, for example, and you want to scale to those large applications without the need to going to the source code manually and have some annotations, because then you could basically already audit the code manually. So let's have a look how the approach that I used in the past 3 years looks like from an overview perspective. And these are separated in 5 steps. So what we first do is we take the source code of a PHP application, get all the source code out of the files, and split it into abstract syntax trees. Abstract syntax trees, if you haven't played with them so far, is basically that you tokenize each statement of an application, and then those tokens are connected semantically in a tree structure according to the PHP syntax. Then in the next step, we split the abstract syntax tree whenever the control flow is deferred. So if you have different branches you can take during the control flow of the application, then the abstract syntax trees are divided here and added to basic blocks. So each basic block is single input, single output. There's no control flow defer within one single basic block. And the advantage of this is that we can then analyze the data flow of each basic block separately, because the data flow of each basic block will always remain the same. And then we can summarize what we have analyzed for each basic block in this block. So we analyze the data flow of one basic block and then store the analysis result in this basic block. And we do this because then when we connect those basic blocks to a control flow graph, the edges here are the constraints for the different execution paths, then we can perform data flow analysis based upon the block summaries, and we don't have to reanalyze what's happening in those basic blocks. So we can just analyze on those summaries. And once we analyze the whole control flow graph of a function, for example, we can create a data flow summary of this function and store the data flow summary and connect the summary of this function to this function. So whenever the function is called again, we can just reuse the summary again. And we don't have to reanalyze the whole function. We perform backward circular taint analysis. That means whenever we find some sensitive operation, for example, a SQL query is executed, then we try to resolve where does the arguments come from used in that SQL query, and if they stem from user input, then we have a security vulnerability. This is like the high-level overview of the static code analysis approach we are using here, and I'm going to go a bit more into detail in different steps. So what we then do is we refine this basic concept in another 3 steps in order to get the most out of static code analysis. So what we first do is we precisely simulate all those built-in features we are having in PHP. So for example, we have different types of sources, different kind of things. They are relatively easy to configure, but then again, we have thousands of built-in functions that are behaving differently. And we are modeling the data flows through those built-in functions precisely, so we have different plugins running for those built-in functions in order to support, we are supporting 1,000 out of those 5,000, so in order to support those that actually are relative for a security analysis. So you can imagine today there's not only like a source flowing directly into a sensitive operation, so you don't have a get parameter directly used in a SQL query. Maybe it's transformed through multiple of those built-in functions. And you want to make sure to analyze them in detail. Then we use this, as I introduced, this efficient concept of using block and function summaries. And we transported this existing technique also to object-oriented code. So we are assisting our backwards-directed taint analysis with forward-directed object analysis. You will see this later on. So we now are able to analyze object-oriented code and scale to large applications, because Drupal, for example, reaches almost 1 million lines of code, or Magento, so you have today really large code bases you want to analyze. And as a third step, we are detecting security vulnerabilities that cannot be detected so far, for example, the PHP gadget chains. In the end, we support 36 types of traditional security vulnerabilities, as well as combinations for second-order vulnerabilities. And those three security classes I want to talk about in the next minutes a bit in detail. So let's start easy how we detect first-order security vulnerabilities. And first-order basically just means those are the traditional vulnerability types you all know. So for example, SQL injection, reflected cross-site scripting, they all follow the same concept. We have some user input, we have a sensitive sink, a sensitive operation, and if there's data flow between those 2 points, then we have a traditional first-order security vulnerability, as I like to call it. We also have security vulnerability types that we cannot detect with a taint analysis approach. So for example, if you think of weak cryptography, you can detect weak cryptography with static code analysis, but your scanner cannot decide, is this logically used in something that is that is sensitive for a crypto context, or it's unsensitive. So if you find an MD5 hash, you cannot tell, is the MD5 hash used in something sensitive, or is it maybe just really used for hashing a map? Then we also have to consider security mechanisms. So next to sources and things, we want to avoid false positives. So whenever the developer implemented some security feature, we want to make sure we detect it in order to prevent false positives. And we have some traditional examples here. So for example, the HTML entities function is well known to be a sanitizer against cross-site scripting, but actually it just sanitizes double quotes and the lesser than and greater than sign. So whenever the security mechanism is used in the wrong context, we still have cross-site scripting. So for example, here in line 1, HTML entities is used, and this is safe for line 2, right? Because you cannot use the lesser than sign to introduce new HTML tags. But if single quotes are used, those single quotes are not encoded by HTML entities, so you still have a cross-site scripting vulnerability. And those are the pitfalls Ben already talked about in the previous talk that we want to track and precisely detect with our static code analysis approach. So we don't just want to whitelist and say HTML entities is safe. We want to make sure we look for the context. The same can be applied to SQL queries, for example. If you apply escaping to data that is not actually used in a quoted context, then you still have a SQL injection vulnerability because you don't have to break out of the quotes as an attacker. So as I said, the traditional taint analysis would be, okay, we have some source, we have a sink, and then we have a vulnerability, but we have to refine this to look out for security mechanisms and also to look out for the markup context that is used. And this is called context-sensitive taint analysis. And I'm going to introduce an example now how we are detecting those bugs. So we have here in line 8 this example that we have HTML use with a single quoted attribute. And there are different branches you can take here through the application that is sanitized with HTML entities or typecasted. So we will transform this code into our abstract model and our abstract graph model. We illustrate it in this way here. Let's say this is our control flow graph. And then our analyzer detects a sensitive sink. So we have the echo statement, and the echo statement is known to be affected to cross-site scripting. So we invoke an HTML markup parser. And the HTML markup parser tells us precisely I detected a div element with an ID attribute, and it uses single quotes. Then we look where those arguments stem from. So we first take the left branch here, and we see, okay, there's a typecast, this is secure, so we can stop our analysis here. And then we take the other branch and look where does the ID variable can be resolved to. And we detect this HTML entities function. And we do not stop here, we just simply assign sanitization tags to this data symbol ID. So basically this is our representation here, and we say, okay, HTML entities sanitizes against double quotes lesser than sign, so we apply two sanitization tags here. And then we continue our backwards directed data flow analysis, and then we see, oh, okay, we have user input, so this must be a security vulnerability if there are no sanitization tags applied for this context we detected. So we saw we have a single quoted attribute context, but we have only sanitization tags for the elements and for the double quotes. So this is a cross-site scripting vulnerability, although HTML entities was present. We actually did some studies. So we did a study paper where we have 25 applications. They had like on average 100,000 lines of code, and we analyzed which markup contexts are the most popular. Of course, this was HTML because PHP applications are designed to print HTML code, and we have some SQL queries. And then we could make some nice statistics which markup contexts occur more popular than other markup contexts, and also observe where are security mechanisms applied wrongly or more wrong than other security mechanisms. I'm not going into detail for all of those bars, but for example, we could see for a double quoted tag here for HTML, there's mostly converting use. Converting here is HTML entities, for example, that converts HTML characters. And whenever the developer decided to build something himself with regular expression validation, or some replacing, where the developer tried to replace some character, then they were more prone to security pitfalls than using other security mechanisms. And the same for SQL injection. Again, I'm not going into detail here, but just for example, the escaping was used correctly next to type validation for single quoted SQL queries. But whenever there was no quote used, there was still the escaping applied sometimes, and we could detect those security vulnerabilities. So we could make some nice statistics and then also use those statistics to improve our tool by saying, okay, we focus on markup contexts that are more frequent than others. So we have the markup frequency here with this line. This means HTML double quoted context is the most popular markup context, and the URL attributes are less popular, although they are more affected by security vulnerabilities. Those are the bars. And then we could see, okay, maybe we focus on those three in the middle. So whenever we see a JavaScript tag, this is more prone, like user input within JavaScript text, this is more prone to security vulnerabilities, or HTML text with a single quotes used, more prone to security vulnerabilities than other attributes. So we have a little demo now. So in the end, we found remote code execution. This was found by the Q53 guys using our tool. I think it was last week. And they found a remote code execution vulnerability in the latest PHP version, which is fixed now. And let's just see how this could look like. So just quickly type in here PHP So this is how the interface could look like for those code analysis techniques. And then we have an initial phase where the code is transformed into those graph models first. So we have this parsing phase. So the code is split in those abstract syntax trees, the control flow graphs are built, the summaries are built, and this is the first phase. And then we see here, for example, like a heat map where we say, okay, there are no security vulnerabilities detected so far. And then our next phase begins, now the actual scanning phase. And whenever we find security bugs, we can list them here on the left side. And our heat map also should increase in a minute, or in a second, I hope, not a minute. Let's see what happens. So basically, PHP-MyAdmin here has about 250,000 lines of code, so it's quite large. So it takes a while to analyze, but the whole scan in total still takes only 3 minutes to finish on my laptop, so it's quite fast. And okay, SQL injection is not that interesting in PHP-MyAdmin, right? Because you can execute SQL queries anyway. But also shortly, there's the code execution coming. We can have a look at the code execution vulnerability already while the scan is still scanning. And then we can see, okay, which parameter is affected by the vulnerability, the post parameter find. And in the end, it was used in a preg replace, so where you can truncate with a null byte the regular expression and append an eval modifier in PHP, and then the second argument would actually be evaluated as PHP code, and we would have this code execution vulnerability. Okay, this was a short demo. Let's see, okay, the scan is almost finished. As we can see, there are some, actually PHP-MyAdmin has thousands of SQL injections, but we also reported them, but nobody cares about them, so they will just stay there. Okay, so let's have a look how we detect second-order security vulnerabilities. So second-order security vulnerabilities, for example, persistent cross-site scripting, basically mean for us from the perspective of static code analysis that we have some user input, but on the first operation, this is sanitized, right? So if the payload is stored, for example, in a database, then it is safely written to the database first. There's no SQL injection going on. It's safely stored in the database, and then in the second step, the application might reuse our payload we stored in the database, and we have a second-order vulnerability. And we also call or introduce the term like multi-step exploits. Basically, it's just a term for the case where you have some user input triggering a security vulnerability, and the security vulnerability allows you to taint more persistent data stores than the application's logic would actually allow you to do so. So for example, if you have a SQL injection in an insert query insert SQL query, then you can taint more columns that you can actually write to, and then the application might assume this is like a static column with static values, and then we have a second order, we have a multi-step exploit because you're exploiting in the first step something, and then we trigger another vulnerability. Just for the terms. Of course, this can be used with all different kind of combinations with user input, with persistent data stores, so not only databases, also file names if you have a file upload, or the session variable, which is basically file content by default. And then you can have all kind of combinations for second order vulnerabilities. So let's get back how we analyzed for first order vulnerabilities, and then we see what's different to detect second order vulnerabilities. So let's say we have this insert query here, so we try to resolve where the variable name, for example, comes from. So we have our analysis model again, and we see, okay, name comes from user input, so we trigger our SQL injection vulnerability report in a simple example. Now what happens if there is sanitization in place? We have the sanitizer here. It applies escaping, so there is no SQL injection. So our analysis will tell us, okay, there's no SQL injection here. But since we are invoking those markup parsers to tell us which context is used, and we are also doing this in SQL queries, we see that, okay, our SQL markup parser can then also tell us not only the position, but also is it like a writing SQL query or a reading SQL query. So it can tell us, does it use select, insert, update, whatsoever. And then we can use this information and say, okay, this is writing to the table users, and the first column is tainted. So we store this in our analysis environment. We let our scanner know table users, the first column name here, this is possibly tainted by user input. And for the detection of those multi-step exploits, we simply extend the analysis for a SQL injection in an insert query, and we say, okay, we have SQL injection insert query, that's great, because then as an attacker, we can also taint all upfollowing columns. So in the column row, there's not only the admin and user anymore, static values, but also the attacker can write some data there. And then as the second step, whenever we detect that data is read from the database or from a persistent data store in general. We detect this by doing the following. Whenever we resolve from a sensitive sink, for example, the echo operator, the data, and we see it comes from a persistent data store, there's some reading going on, then we create a temporary vulnerability report. And we say, okay, we have here the table users and the column name that is selected, and we don't know yet if that's a security vulnerability, but we store a temporary security vulnerability report. And in the end, we can connect those collected readings and writings to persistent data stores and then see is this temporary vulnerability report indeed a security vulnerability. So we check, is the column name stored in our analysis environment as tainted? It is. Is this data stored here sanitized against the vulnerability type we found? Because the developer could decide to store sanitized data into the database. And if that's not the case, we can create a second order vulnerability report. So for example, we found a remote code execution vulnerability in combination with other bugs in OpenConf. This basically looked like that you could abuse a SQL injection or cross-site scripting vulnerability to gain administrator privileges. And as an administrator, you could change a header file value in the database. And the header file database value, you could point this to a paper you uploaded to this platform. So I have to add OpenConf is a conference management platform, so you can upload your own papers there, store the PHP payload in this paper, and then point the OC header file value to this paper, and then you would have the remote code execution vulnerability. So now you might say, okay, OpenConf, who uses that? OWASP, for example. So if you want to apply for, but it's safe. Okay, now for the last part, the gadget chain detection. I first go quickly into PHP object injection. I know there was a talk already about object injections or unserialized vulnerabilities in Java. This is similar to PHP. So basically, the attacker can inject an object into a PHP application and stack multiple objects in the object he is injecting. And based upon the objects he's injecting, the control flow is deferred to different methods of different classes. So to illustrate that, we have here a white object, a green object, and a blue object, and the control flow is then deferred to the white class, green, and blue class to, in the end, trigger code in the red class where some sensitive code can be reached. So to put this in an example, we have the class text here. We have the serialize feature in PHP that basically can take an object and turn it into a unified string representation, the serialize format. So we serialize this object text here, and then this will be the serialized string format. And we have a PHP object injection vulnerability if the attacker can modify the serialized string format. So then the attacker is able to change the class, for example, or the data that is within this object. So you cannot inject own PHP code, but modify an existing object that is transferred through the different states of the application. So the attacker would inject here a different class type, for example, or a different property. And if this data is unserialized again, then this object contains the data actually injected by the attacker. So this is how PHP object injection works. And now the interesting part for PHP are those magic methods, because those are called automatically upon specific events, and if they're defined in classes by the developer. So next to the constructor as the magic method, we also have destructors. And if we have, for example, the class file here that defines the destructor that deletes a file based on the property file name, we can modify this class text here to file and add the property file name and point it to a file we want to delete. If this string is unserialized, then this file object is created, the destructor is invoked, and then the file name property is used in the file deletion here, and we can delete arbitrary files. Now, property-oriented programming comes in handy if there is no magic method, for example, such as a destructor, that contains actually sensitive code. But it could be that this destructor is pointing to different code locations based upon a property. For example, here the handler property. And this handler property allows us, because it's under the control of the attacker, to jump to arbitrary close methods. So if we have, for example, here the interesting class process that on the close method calls a system command, then we can inject the process class into this property here, and then the close method over here will be called, and we can reach the sensitive code that wouldn't be otherwise reachable. And this is how we can chain those gadget chains or those gadgets together to reach sensitive code, as illustrated here. Then we can terminate the command and inject arbitrary commands and have our command execution. Okay, there was a quick intro to PHP object injection vulnerabilities you already probably knew, but how do we check those PHP object injection vulnerabilities and those gadget chains now with static code analysis? So PHP object injection basically is like a first order security vulnerability. So there's no difference in detecting a SQL injection, for example. We have our sensitive sync unserialized here, and we look, does that stem from user input? Then we can simply trigger our PHP object injection vulnerability report. The new thing is now that whenever we detect those PHP object injection vulnerabilities, the return value of an affected unserialized built-in function is a flagged object, and we flag this object as tainted because the attacker can control all properties, so this object is flagged as tainted. And then we propagate this object forwards directed through our analysis environment, and if this object is used or properties are used of this flagged object, then we know instantly, okay, we have a security vulnerability here. So how do we detect those gadget chains now? Whenever we detect a PHP object injection vulnerability, we automatically invoke the analysis of specific magic methods that can be invoked by an attacker. So for example, our destructor method here, we invoke the interprocedural, the function analysis of this magic method destruct here, and we perform analysis of this method, and we see, okay, we don't know where this close method is called from, so we invoke the analysis of all close methods throughout the source code. So we, for example, analyze then the method close of the process class we already seen, and for example, this close method of a database class. And for those methods, again, we perform our taint analysis. So for example, we have the system call here. We try to resolve the PID property. It cannot be resolved, so it's stored as a sensitive property of this method. We store it in the analysis environment. For this close method, there are no sensitive properties because nothing security sensitive is going on here. And then once we collected those sensitive properties, we apply those sensitive properties back to the call side. So here the class close method was called here. So we apply those properties back to the handler property, and then we know this destructor is affected by system command execution for the PID property applied to the handler property. And then at the call side again, where our PHP object injection happened, we apply those properties again, and since we already introduced that a flagged object says that each property that is touched automatically triggers a security vulnerability, we can apply, when we apply the PID and handler property to this flagged object, we automatically have our gadget chain that reports us the remote command execution chain, and then we can connect this report to the PHP object injection. So a bit earlier, we found, for example, a PHP object injection in Joomla that allowed to execute arbitrary commands during the installation process, but not only for administrators, also for remote attackers. Okay, so to come to the conclusion, we've seen that the requirements for static code analysis tools changed. So we have diverse language features we have to analyze precisely in order to detect those security mechanisms, for example. There are also encodings and decodings we want to keep track of to really precisely connect those built-in features and see how they react upon the markup context. And we have those complex security types. We have second-order vulnerabilities, multi-step exploits, gadget chains we also want to detect. And this has to be detected in growing code size. So we also could show that our static code analysis approach works for the automation of bug detection. We can quickly identify traditional security vulnerabilities such as cross-site scripting and SQL injection, but also more complex types. And remaining challenges, for example, are frameworks. So where a lot of reflection is going on, you are always hindered a bit with static code analysis to detect those reflections, or for example, template engines. And here some framework-specific models have to be applied, or can be applied as one solution. That's it, and thank you for the attention. So are there any questions?
Yeah, so for second order vulnerabilities, sometimes the input comes from different apps or APIs. So how can we deal with this?
So the question was, how do we detect second order vulnerabilities when the user input comes from other sources than on the web server, right? Well, you cannot know, right? So what you can do is, for example, if there's data fetched from an URL, so the classical example would be a YouTube video, for example, is fetched and then the title is embedded into your HTML content. You could say whenever data is fetched from a URL, then this is assumed as tainted, which is one approach. But I think the best way would be to make a whitelist for then specific domains or not. Because you cannot really tell if this data actually is taintable by an attacker because you don't know what's going on there, right? So YouTube could always sanitize their titles, and you cannot actually inject something there.
Yeah, but sometimes it comes from your own mobile app. So I own an API and mobile app websites, and they all get into the same app source.
Mm-hmm.
So how would I know that this API inserted some SQL and then or JavaScript?
Yeah, then you cannot know unless the static code analyzer also analyzed the other application, right? So if you analyze both applications, then you can combine the analysis results. But if you only analyze one application, then you don't detect actually the writings, just the readings. I mean, you could also configure your static code analysis to say whenever data is coming from a persistent data storage in general, I have a security vulnerability. But I think that leads to too much false positives. So. But that would be one approach.
What's the status of this new version of Perps? Is it open source? Or?
The new version is a commercial product now.
All parts are commercial?
Yeah. Sorry about that. So the question was if we are supporting path sensitivity, to put it short. We do, I would say half. For some constraints, we are resolving those and we are evaluating those. So if you have input validation within the constraints, for example, the if is numeric and then something is checked and we detect it. But for other things, we are path insensitive. So an example would be if you have an error variable and this error variable is set to false, and for different paths, then you set it to true or to false or to true. And then it's something completely different going on, and in the end, it checks if this error variable was hit to true or set to true or to false. Then this is like two different contexts, and our analysis would only analyze the security vulnerability, but would fail that there's something security independent going on with this error flag variable and detect the security vulnerability. And there would be a false positive then. Oh, good point. Thank you.